Hi, this is Shoikat Majumdar. Today we will discuss the different statistics. First, we will start with the classical statistics as proposed by Maxwell. Now, in this module 5 of Statistical Mechanics, today's topic is Maxwell-Boltzmann statistics. The learning objective is to compute macroscopic properties from the quantum mechanical information about the atoms and molecules of interest. Different formalisms in statistical mechanics. We have already discussed few of the formalisms in our previous lecture. We are discussing in a different way in the light of classical statistics. The various methods of statistical mechanics are applied to discuss some average or most probable properties of large assemblies of electrons, atoms, molecules, etc. Before the advent of quantum mechanics, Maxwell, Boltzmann, Gibbs and other scientists applied statistical methods with the help of classical physics. These methods are collectively known as classical statistics. Maxwell-Boltzmann, or commonly known as MB statistics, is classified as classical statistics. These statistics were proved to be successful in explaining pressure, temperature, etc. of the gaseous system. But this couldn't explain some experimental results like energy distribution in case of black body radiation, specific heat at low temperature, etc. For explaining such phenomena, Satyendranath Bose, Albert Einstein, Enrico Fermi, Paul A. Dirac has made use of some new statistics with the help of newly discovered quantum theories. Newly discovered quantum theory means it was discovered around 1901. Max Planck proposed during the black body radiation, explanation of black body radiation. So after that, this quantum statistics came into force. So again we can show this figure. Statistical mechanics can be broadly classified with two types of statistical mechanics. One is classical statistics. Maxwell-Boltzmann statistics falls under this criteria. Another one is quantum statistics, Fermi-Dirac statistics and Bose-Einstein statistics fall under the criteria of quantum statistics. Now let us start with the postulates of the Maxwell-Boltzmann statistics. The basic postulates of Maxwell-Boltzmann statistics are: number one, the associated particles are weakly interacting and distinguishable. That means we can distinguish the particles. That means suppose there are different balls of same size, same shape, but the colors are different. Say red color or blue color or yellow color. So this can, we say, as distinguishable particles, but they are weakly interacting. Number 2, the particles do not obey Pauli's exclusion principle. That means the particles are not obeying the exclusion principle. So from this, number 3 postulate is each energy state can accommodate any number of particles. That means in any energy state, any number of particles can be accommodated. Suppose there are 5 energy states. Suppose the first energy state having 1 particle, second having 2 particles, third having 5 particles, fourth there is suppose no particle, fifth suppose there is 1 particle. So this is how it is arranged. So any number of particles can be accommodated in any energy state. Number 4, the total number of particles in the entire system is constant. That means suppose there are 20 particles in 5 energy states, so it is constant. Number of particles, it will not be changed. Number of energy states, it will not be changed. Only change is accommodation in the energy states. Number 5, the total energy of all the particles in the entire system is constant. Suppose in the energy state U1, number of particles is N1. So total energy for the state is N1 E1. Second state E2, number of particles N2. So E2 into N2. So total energy is E1 N1 plus E2 N2 plus E3 N3. In this way, the total energy of the system is constant. And final one is the particles are spinless. So these are the postulates as a whole for Maxwell-Boltzmann statistics. Now, which particles can follow the Maxwell-Boltzmann statistics? Ideal gas. Ideal gas will follow the Maxwell-Boltzmann statistics. Or we can say gas molecules at high temperature and low pressure will follow the Maxwell-Boltzmann statistics. Particles, those obey Maxwell-Boltzmann statistics, are known as bosons. Bosons are the particles which will obey or which obeys the Maxwell-Boltzmann statistics. Consider a system composed of n distinguishable. Distinguishable means the particles we can distinguish differently. Suppose red ball, yellow ball, white ball, this way, and non-interacting. They will not interact. Let out of these n particles, n1, n2, n3, n4, n5 up to ni particles are to be distributed in the energy level. Suppose N1 particles are distributed to U1 energy level, N2 E2 energy levels, N3 E3 energy levels. In this way, Ni particles in Ei energy levels respectively. And these energy levels have Gi, that means G1, G2, G3, G4 up to Gi, one number of quantum states corresponding. So total probability for a given distribution can be calculated as W is equal to Gi to the power Ni. Now this W represents the thermodynamic probability. That means number of microstates in a given macrostate. Gi represents number of quantum states and Ni represents number of particles. Now the Maxwell-Boltzmann distribution function is given by SEI is equal to Ni by Gi is equal to 1 by e to the power alpha plus beta EI, or we can say Ni is equal to Gi by e to the power alpha plus beta EI, or Ni is equal to Gi e to the power minus alpha plus beta EI. This alpha and beta are two multipliers. This is we will get to find out this distribution from Starling's formula. Now, the calculation part of this Maxwell-Boltzmann distribution is beyond our scope. So just we have to remember the function or distribution function Fe is equal to Ni by Gi is equal to 1 by e to the power alpha plus beta Gi, which physically gives the probability of a particle to occupy the energy state Ei. So distribution function means the probability of a particle to occupy the energy state Ei. Now the total number of particles n is equal to n1 plus n2 plus n3 up to ni. So n1 is equal to, from this formula, n1 is equal to this, if put I is equal to 1, this is g1 by e to the power alpha plus beta e1. If you move it in the numerator part, then e to the power minus alpha plus beta e. So write it here. N1 means g1 e to the power minus alpha minus beta e1. N2 means g2 e to the power minus alpha minus beta e2. N3 means g3 e to the power minus alpha minus beta e3, and so on. Taking common e to the power minus alpha, so it becomes summation of gi e to the power minus beta ei. I is equal to 1 to up to n. So n is equal to this, n is equal to e to the power minus alpha, and we are representing it as z. This z we will say as partition function. Z is equal to gi e to the power minus beta ei. So for Maxwell-Boltzmann distribution, the partition function is gi e to the power minus beta ei, where gi is the quantum state, beta is the multiplier. Already we have discussed the values of multipliers alpha and beta depend upon the physical properties of the system. We get from the equation e to the power z is equal to n by z. From this equation, e to the power alpha is equal to n by z. So this will be e to the power alpha. This will be e to the power alpha, not e to the power z. E to the power alpha, e to the power minus alpha is equal to e to the power minus alpha. E to the power minus alpha is equal to n by z. After substituting the value of e to the power minus alpha, the equation can be written as ni is equal to, changing e to the power minus alpha by n by z is into, here it is e to the power minus alpha, we are replacing e to the minus alpha by n by z, gi e to the power minus beta ei. Now consider an example. A gas has two distinguishable identical particles in the kth energy level, in which there are three quantum states according to Maxwell-Boltzmann statistics. Find the possible number of microstates and find also the number of microstates in tabular form. To answer the first one, there are three quantum states, that means gi is equal to 3. And number of particles is 2 distinguishable identical particles. So we will apply Maxwell-Boltzmann statistics, and the formula for calculation of microstate is W is equal to gi to the power ni. So gi is 3, ni is 2, 3 square is equal to 9. So possible number of microstates will be 9. Now comes the second part in tabular form. There are three quantum states. 1, 2, 3. We are representing it as 1, 2, 3. And two particles. And the particles are distinguished. So the particles are A and B. Microstates are first. Suppose there are two particles. In 2 there is no particle. In 3 there is no particle. So if there are only two particles, A and B, both particles will be accommodated in this quantum state. Come to the second microstate, 0 to 0. This microstate is 2, 0, 0. And 0 to 0, in second quantum state there are two particles. In first quantum state and third quantum state there are no particle, that is 0. So this is no particle, AB, and no particle. Another microstate is 0, 0, 2. 0, 0, 2 means in the quantum state 1 there is no particle. In the quantum state 2 there is no particle. In the quantum state 3 there is two particles, and these two particles are A and B. Now another microstate is 1, 1, 0. When 1, 1, 0, there are two particles. In 1 you can represent A, B, and no in 3, no particle in 3. Just reverse this one. B in quantum state 1, A in quantum state B, on quantum state 2, and in 3 there is no particle. So there are, for 1, 1, 0 microstate there are two microstates, and 2, 0, 0 there is one microstate, there is 1 micro. 0 to 0, 1 micro. 0, 0, 2, 1 micro. Now come to the microstate 1, 0, 1. So number of quantum states in quantum state number 1, particle A is there. In quantum state 3, B is there. In quantum state 2, there is no particle. So similarly, reversing this one, B, no particle, A. So again for 1, 0, 1, there are two microstates. For 0, 0, 0, 1, 1. 0, 1, this is incorrect. 0, 1, 1. For 0, 1, 1, this one will be 0, A, B, reversing B, A, 0. So this one will be 0, 1, 1. So here in this case, we are getting 9 microstates. 1, 2, 3, 4, 5, 6, 7, 8, 9. There is only one incorrect. This is 0, 1, 1. Last one is 0, 1, 1 microstate. Disadvantages of Maxwell-Boltzmann statistics. It is considered that the particles of a system, for example ideal gas, are distinguishable. So it can explain the energy distribution of the molecules of ideal gas to a fair degree of accuracy. But it is failed to explain the energy distribution of indistinguishable particles like electrons, so-called electron gas, or photons. Indistinguishable means, suppose there are 10 balls having same color, say blue. So how can we distinguish? So distribution of this type of particles, just like electron gas, photons, this cannot be explained by the Maxwell-Boltzmann statistics. Degeneracy in statistical mechanics. In statistical mechanics, the word degeneracy is also used to indicate the deviation from classical results, apart from its conventional meaning. The deviation from classical results depends on the occupation index Ni by Gi. So Ni by Gi is known as the occupation index. As we have already shown in our previous slides, a system is said to be strongly degenerate when Ni by Gi is very greater than 1. It is seen for Boltzmann particles. A system is said to be weakly degenerate when Ni by Gi is just greater than 1. And it will be non-degenerate when Ni by Gi is very less than 1. So, Ni by Gi very greater than 1. This is the classical statistics. Classical statistics. Other than this, these are the quantum statistics. So, weakly degenerate when Ni by Gi greater than 1 and non-degenerate when Ni by Gi is very less than 1. Another example. A system has non-degenerate single particle states with 0, 1, 2, 3 energy units. These particles are to be distributed in these energy states such that the total energy of the system is 3 units. Find the number of microstates if the particles obey Maxwell-Boltzmann statistics. Find the corresponding macrostates and microstates also. So we have 4 energy states. One is 0, that means 0 E. 1 means 1 energy. 2 energy. 3 energy. Now we have the number of particles 3 particles this state. So we will representing these 3 particles as A, B and C. As already it is stated, it is following Maxwell-Boltzmann statistics. That means the particles are distinguishable. Now suppose we have total energy, we have to place the particles in such a way so the total energy becomes 3 epsilon. So if we place 2 particles in the 0th energy level or 0th quantum state and another particles 3e quantum state, then it becomes 2 into 0 means 0 and 1 particle in 3e means 3. So ultimate total energy is 3. So the macrostate is 2, 0, 0, 1 and the corresponding microstates are here AB, C, then ABC, BCA, CAB. So there are, for this macrostate, there are 3 microstates. Next combination is here 1 particle, here 1 particle, here 1 particle. So 2 into 1 means 2e, 1 into 1e means 1e. So 3e, 0 into 1 means 0. So 3e will be the total energy. So representation of macrostate is 1, 1, 1, 0. And microstates are ABC 0, BCA 0, CAB 0. Now altering this one. ACB 0, BCA 0, CBA 0. So there are the 6 microstates having total energy 3e. And last one is, if we put 3 particles here, then there are no particles in this energy states. As per Maxwell-Boltzmann, we already know any number of particles can be accommodated in any energy state. So we are placing 3 particles here. So 3 into 1 means 3, here 0. So there is only 1 microstate. So total number of microstates is 3 plus 6 plus 1, that means 10. So total number of microstate is 10. This is not 9. It is incorrect. This one will be 3 plus 6, 9 plus 1, 10. So this is how we can represents the particles in different quantum states, and correspondingly you can find out the macro states and their micro state and total micro state also.